Thank you for attending our talk. I'm very happy to present this work on private interdependent valuations. So this is a joint work with Alon, Michal, and Divyarthi, who are all there. So if you have questions, you can also ask them. Let me start with a quick motivation. So interdependence captures auction settings where people don't actually know their own value. Because imagine a resale mall or an art painting. If it's a true Picasso painting or if it's a fake one, that will impact your value, and someone else might know about this fact, but you may not. So this is the kind of motivation we're interested in this book. And so to model this, let me directly start with the formal model. So as input, we're going to be given n agents, and it's going to be a single item auction. So I want to select one agent. And each agent is going to have a private signal, which represents the information they have about the item you're selling. And they will also have a private valuation function that will aggregate all the signals into their value for the item. And so all of these things are held by the agents, and they're going to report that to you, and you want to design a truthful mechanism to allocate the item. So what is formally the output? We're going to see that we need to use randomization. So it's going to be a distribution over the agents. I'm going to select one at random according to some distribution. That's going to be my allocation. My objective is going to maximize the social welfare. So that's the expected value of the buyer who gets the item. So I want truthfulness. I'm going to define later what I mean by that, but this is going to be a mechanism design talk. And finally, we're not going to be able to allocate exactly all of the time the item to the person with the highest value. So we're interested in the approximation ratio, which captures like how far we are from the optimal. So it's an upper bound on this ratio of opt, which is the max value, divided by the social welfare of our mechanism. Right, so this was the model. Let me quickly tell you why this is a hard problem. So look at this example. This is an example where everyone else can decrease other agents' value. Let me make that a bit more formal. Every agent will have a signal. Here, S1 through Sn are all signals equal to 1. And all the values are going to be equal to the product of all of the signals. So our mechanism has to take care of that, right? And so because this instance is symmetric, there must be one agent who doesn't have more than a 1/n probability of getting the item. And if that person were to lie and misreport something else, we shouldn't give them more often the item, because that would be a successful manipulation, right? And so in particular, if agent 1 decides to report a signal of 0, everyone else's value will drop to 0 because we took the product. But they can also change their valuation function so that they don't have a value of 0, and the mechanism would be forced to give them the item. So now the mechanism doesn't really know in this situation if the agent was lying or not, and doesn't exactly know what to do and cannot do better than the n approximation. That's the main intuition of this example. And why am I using this example? It's because in our setting, valuation functions are private. And if you can see that the successful manipulation involved changing valuation function, but most of the previous work only considered the public valuation setting where only the valuations, the signals were private. And these types of instances would have been easy to solve because if you check, there is a strong condition called single crossing, which is satisfied by this instance, which would give us an optimal solution if valuation were to be public. Okay, so we have a hard problem, and also this is a hard instance. So we need to have some additional assumption to be able to solve this problem. Otherwise, n approximation would be a boring end of the story. So we're going to add one assumption, which is going to be that the signals are not going to be complements. So I'm going to prevent this phenomenon of everyone being able to decrease my value by assuming some structure on the valuation function. And the definition we use here is the submodularity of a signals property that also has been used in auctions with public interdependent values. So one property satisfied by SOS valuation, submodular over signals, is that our valuation functions are going to be self-bounding. So I'm going to come back to this a bit later, but from now on, you can assume that our valuation functions are going to satisfy these properties. Okay, so I told you about the problem we consider, the assumption we make on this on the valuation functions, but I haven't told you yet what I mean by truthfulness. So we want to design an incentive compatible mechanism. And so the notion of truthfulness we're considering is that of ex post in the incentive compatibility. So we want truthfulness to be a Nash equilibrium. If everyone else's report their true signal and their true valuation function, I want it's an optimal solution for me to also report my true value. And so this is the solution concept. And in a previous work, a sufficient condition was given to how do we satisfy this condition. And it's imagine every probability function xi only depends on s minus I, which is the signal of the other agents, v minus I, which are the valuation functions of the other agents, and vi of s, which is my value evaluated on all of the signals. So it cannot really depend in a complicated way on my signals, on my evaluation function. It has to only depend on my value and maybe on what other people report. And more importantly, I want my probability to be increasing in my own value. This is to be able to use a Meyerson's lemma, which will give me some prices that I can use to make truthfulness a best response strategy. And so in this previous work by Alon and Kira here, they also show that this condition is almost necessary.
And Sharon.
And Sharon, who's online probably. Okay, so how do we develop a mechanism who satisfies this sufficient condition? Let me give you the meta construction that is used in most of the works on this problem. So we're going to consider an assignment function, y, that will take as input some weights. So each agent j has a weight wj, and we're going to select agent j with a probability equal to y sub j of weights. And we want that the probability of an agent j is non-decreasing in w. Like if we increase the weight, we also increase the probability. That's going to be related to truthfulness. So this is like our building block. We're going to try several building blocks. And from these building blocks, we're going to define this meta mechanism, which uses this assignment function y. So how does it do that? So the probability xi, so the probability xi is going to be the assignment function, the assignment of in some instance wi, where the instance wi is defined as taking the true value for agent I and what we call low estimates for other agents. So one thing which is very important here is that our weights wi only depend on other people's signals and valuation function, except maybe for my own value, which is my own weight. Right, so this yi of wi means I'm taking the probability of agent I in the instance defined by the weights wi. And I'm going to renormalize that by some factor c. And so the main challenge is going to choose c such that our mechanism is what we call feasible. Okay, what could happen? What could happen is because we're solving this problem, this assignment function for different weight function, maybe I will be computing something which is not really a probability distribution. I might over-allocate the item, and so that's why I have to renormalize by this c. And so the main challenge is giving a proof that with such a c, we have a feasible mechanism, and also choosing this assignment function y such that it's robust to small changes in weights. Let me give you an example for this. Okay, before that, let me just recap quickly existing results. So we have this meta mechanism that was used in the first work that considered private interdependent values. That was a breakthrough paper because previous works only considered public valuation function, and they were the one who defined this private valuation idea. and they came up with the log square n approximation where they were able to bound C using the chromatic number of as a cute proof. Later, in a subsequent paper, after a lot of hard work, we managed to find a constant approximation. If you want to hear more about this, Divya here is going to give a talk about that in the highlight beyond this C talk. Go to her presentation, it's going to be great. And so we managed to bound C using a closed formula for this Y function, but that was a lot of computations. And in this work, we're quite happy with our new construction because the proof goes through a nice idea which uses some linear programming and the dual of some linear program to bound our feasibility constraints. And we hope that it's going to be helpful to generalize maybe to other settings. Okay, so this is the overview of previous results. Now let me jump on an example. Okay, so what could go wrong if I choose my assignment function not in a correct way? So y is this assignment function. Let me just choose y to be the argmax function. I just take the highest weight and I give them the item. Okay, if there is multiple highest weights, I can randomize between them, but that's not really important. So here, what I drawn on the bottom of the slide is for each agent I, we consider some instance with their own value and other people's low estimate. So that's what I represent by these dotted lines. And so we're solving this assignment function for every I, and we're taking the probability value of each agent in their own subinstance. And so here you can see in I's instance, I is the best. In the star instance, star is the best. In the square instance, square is the best. In the triangle instance, okay, star is the best. But one thing that could be bad is that each person could win their own instance. And here we'll have to choose a C equals to N if we want to ensure feasibility, which would be terrible in terms of approximation, because N approximation is just giving the item to one person at random. So we don't want that to happen. And that was happening because the assignment function is really discontinuous. If I just become better than someone else, I get all of the probability. So, but this is not happening thanks to the assumption that we made earlier. So remember, I told you that we're assuming submodularity over signals, which implies something called self-boundingness. So here on a picture, here is what it means. So here is the value of the star, and also the low estimate of the star in other subinstances. And so if you sum up all of the decrease in other instances, you can see that it doesn't exceed the value that the star had in the beginning. And so this is one property satisfied by submodular valuation function, and it holds for all of the other agents. So we can use this property. And in particular, in the previous example, we may be able to use the fact that values don't change too much to choose some assignment function which is a bit smoother than our hardmax, and to allocate the item that way. Okay, so because the value don't move too much, our idea was to use to borrow some ideas from this probabilistic serial mechanism, which is an assignment mechanism used in matching, where let's say each person is going to eat the item at a constant rate, but they're going to start at different times depending on their value. So the person with the highest value is going to start eating first, and through time, at some point, we will reach another value and other people will start eating. And once a full probability of 1 has been eaten, we can stop the mechanism and allocate using the probability that we have here. And so because in other instances, I'm not changing too much the value of others, I'm also not changing too much my own probability. So the intuition here, we can make this a bit more formal. If you start from the instance on the right, where you have all of the real values, and you decrease someone else's value to be their low estimates, if we decrease it by some delta value, a person who gets the item doesn't increase their probability more than a delta over n, because there is a lot of people eating at the same time this probability share. And so if the sum of y was 1 in the beginning, because it was a probability distribution, and I'm only increasing by the total amount of decrease, I should get at most a probability, a sum of probability of 2. So setting c equals 2 should work. Actually, it doesn't exactly work, because here the intuition I gave you only works if everyone receives a positive probability in the instance, or if we scale the instance properly that the max value was 1. But we can make it work with a more complicated construction, where we will start eating at a time that depends on the log of the value and not on the value. And we also need to formalize a bit better what is the value of this probabilistic serial. And for that, we're going to write a linear program. So you can check, or you can trust me, this program PI is computing the probability of I in the probabilistic serial mechanism. And our goal is to bound the sum of probabilities. And so linear programming is great for that, because we have the duality as a tool to bound the sum of probabilities. And so our main theorem here is that our mechanism using this probabilistic serial assignment function is going to be a truthful 5 approximation. Truthful because we use the construction with the meta mechanism. 5 approximation because first we bound the sum of probability by 4. So we divide everything by 4. So we lose a factor 4. And second, we have a factor 4 over 5 because our mechanism is not exactly always giving it to the highest person. So we're also losing a bit on the fact that probabilistic serial is not exactly optimal with private values. Let me wrap up with a last slide. So here I only presented one of the results in our paper. It was a 5 approximation with private SOS valuation, but we also have other results, in particular with Matroid. So in all of these interdependent auctions, one thing that clearly helps to design mechanism is this single dimensional property where each buyer has one value that may depend on signals, but they only have one value. And so to generalize that, we could also try to select an independent set from a Matroid, and we can make it work for some valuation functions. Open problems, can we improve the upper and lower bounds? So here there is a gap between the lower bound, which is 2 from the public setting, and the upper bound, which is 5. Can we improve the Matroid one? Can we try interdependence with other optimization problem? Before finishing, if you want to hear more about private interdependent values, we also gave a tutorial in the preview week of EC, so you can check the video when they will be on YouTube. And once again, Divya is giving a talk in 2 hours, so go to that highlight session. Thank you.